Greetings students, Mr. Courtney here. In this video we're going to be looking at the mole concept, and specifically we're going to start looking at percent composition. In this video we'll introduce the mole, what is the mole, what is it used for, then we'll calculate formula mass, calculate percent composition, and we'll also look at how to calculate the mass of an element given percent composition. So we start with formula mass. Formula mass refers to the mass in grams of 1 mole of a pure substance. And when we say pure substance here, it can either be a compound, element, or ions. So when we talk about a substance, it could be compound, element, or ion. Now, there are different names that we come across for, or we use to represent formula mass. You may see molar mass, molar weight, molecular mass, molecular weight, formula weight, gram formula mass, and gram formula weight. What you need to do is be able to recognize these as meaning the same thing as formula mass. So again, formula mass is the mass in grams of 1 mole of a pure substance. So you may be asking now, what is a mole? What is the mole? So the mole is one of the 7 base units of the SI system. So it's one of our 7 base units that we use in measurement. What does it measure? It measures the amount of a substance. And some people like to say the relative amount of a substance. Now, when we talk about relative amount, we're going to be referring to representative particles. And a representative particle basically means which form does the substance exist in, or what form is that substance found in. Is it an atom? So when we think of atoms, what do you think? We're going to think of the elements on the periodic table. So we can think of like sodium, bromine atoms, chlorine atoms, phosphorus atoms. When we think of molecules, think of ionic compound. Sorry, not ionic, but covalent compound. Water, carbon dioxide, dinitrogen pentoxide. When we think of ions, think of substances with charges, so sodium ions, the bromide ions, chloride, phosphide. When we think of formula units, think of ionic compounds, stuff like NaCl, KCl. Okay, so any ionic compound, we refer to them as formula units. Right, we said the mole is used to measure the relative amount of a substance, or the amount of a substance. And we've used things like this already, because you've used a dozen to mean 12, a ream to mean 500, a gross to mean 144. Now, what does a mole mean? What is the relative amount a mole represents? So a mole represents 6.02 times 10 to the 23rd particles. Remember what we said particles could be: ions, atoms, formula units, molecules. So that's what this represents. Because we have such a large amount of these particles, it's easier to work with the mole than to say we're working with 6.02 by 10 to the 23rd particles. So we don't have to sit and actually count or measure that amount. We just measure based on the number of moles present. And this number, 6.02 times 10 to the 23rd, is called Avogadro's number. So it's going to be important for you to associate this number with the mole and this number with Avogadro's, or as Avogadro's number. So earlier we talked about isotopes, and that isotopes we measure the relative mass in atomic mass units. So now we have one atom of carbon 12. So carbon 12, remember this is the isotope of carbon. We say that it weighs 12 atomic mass units. And then we're saying that 1 mole of carbon 12 atoms would weigh 12 grams. So for an element, what this is telling us, for an element, the atomic mass in grams, all right, is the same as the mass of 1 mole of atoms in grams. So atomic mass, the number that we see on the periodic table for each element, is the same as the mass of 1 mole measured in grams. And we use the unit of grams per mole. So how do we calculate formula mass? What we do is we add the atomic masses together and we round our answer to the nearest tenth. That is the nearest decimal place, one decimal place. So let's look at this example here. We have sodium chloride. So the first thing we should be doing is writing the formula for sodium chloride. And we know that is Na, and it's Na plus Cl minus. So we know it's going to be NaCl. So for sodium, we have one atom of sodium and its atomic mass is 22.990. So that's 22.990. Chlorine, we have one atom also. Its atomic mass is 35.453. So that gives us 22.990 and 35.453. Add these together and that gives us 58.443. Now we said we wanted to the nearest tenth, one decimal place, so that's 58.4, and we units of grams per mole. Alright, in this example we have water, and you should remember the formula for water. That's one that you should know. That is H2O. So for hydrogen we have 2 of it, and its atomic mass is 1.008. Multiply out, that gives us 2.016. Oxygen, we have 1 times 15.999. So that's 15.999. So we add these together, that gives us 18.015. And we want the answer to the nearest tenth, so that's 18.0, and units of grams per mole. So this here is a formula mass of water. Now we have arsenic trichloride. So we have to determine the formula again, and remember, if we see a prefix, so we know it's an covalent compound, sorry. So that's arsenic chloride, and we have 3, so that's a tri. So we have 1 atom of arsenic and 3 atoms of chloride. So arsenic's atomic mass, look on your periodic table. You see that as 74.922. And chlorine, we already know is 35.453. When we multiply these up, we get 74.922. And 35.453 times 3 gives us 106.359. We add these together, we get 181.281. We want to the nearest tenth, so that's 181.3 grams per mole. And there you have the formula mass of arsenic trichloride. Okay, here we have potassium sulfate, and let's go through finding the formula again. Potassium would be K plus sulfate SO4 minus 2, so that's K2SO4. So if we start with potassium, for potassium we have 2, sulfur we have 1, oxygen we have 4. So potassium would be 2 times its atomic mass. If you look it up, 39.098. You can always pause the video and calculate and then come back, check the answers. Sulfur would be 1 times 32.066. Oxygen would be 4 times 15.999. That gives us here 78.196 for potassium, 32.066 for sulfur, 63.996 for oxygen. Add these together, we get 174.258. We want it to the nearest tenth, so that's 174.3, and units of grams per mole. All right, in this one we have ammonium phosphate. So ammonium is NH4 plus phosphate is PO4 minus 3. So that means we need NH4. In parentheses, we need 3 PO4. So for nitrogen, we have 3. Okay, that's 3 times 1. For hydrogen, we have 12 atoms. For phosphorus, we have 1. Oxygen, we have 4. So for nitrogen, that is 3 times 14.007. That gives us 42.021. For hydrogen, that's 1 times 0.1, 12 times 1.008. So that gives us 12.096. Phosphorus is 1 times 30.974. So that gives us 30.974 still. Oxygen is 4 times 15.999. That is 63.996. We add all these together, we get 149.087. We want it to one decimal place, so that's 149.1 grams per mole. There you have your formula mass. Now, the analysis of an unknown compound usually begins with calculating the percent composition of each element in the compound. So that means, what is the mass of each element in 100 grams of a compound? So how we calculate percent composition, we take the mass of the element divided by the formula mass of the compound multiplied by 100. As we see here, mass of the element divided by formula mass, or atomic mass, multiplied by 100. Now we've looked at this before, we just used a different form. It's the same format still. We did part divided by the whole multiplied by 100. Both formulas are the same, just expressed in a different form, and we have to understand that. The mass of the element is what mass does the element contribute towards the total mass, towards the whole, which is the formula mass. So take the part divided by the whole multiplied by 100, we get percent composition. So let's go ahead and look at some examples of these. Alright, in the first example, we're told there are 95.0 grams of barium and 26.3 grams of fluorine in a compound. What is the percent composition of barium and fluorine in the compound? So we're given the individual masses, but we're not given the whole mass or the total mass. So first we need to find the total mass. So our total mass will be the 95.0 grams of barium plus the 26.3 grams of fluorine. That gives us a total of 121.3 grams. So to find the percent of barium, which is our first element, we take the part, which is 95.0 for barium, 95.0 grams divided by 121.3 grams, and we multiply that by 100. If you calculate it, that would give you 78.3%. Now to find the percent fluorine, percent of fluorine. Since a percentage is out of 100 and we only have 2 elements, that means the 2 of them must add to 100. So if we subtract 78.3 from 100, that gives us the percentage of fluorine, which is 21.7%. Alright, in the second example, we're told if 225 grams of a compound that is known to contain only, the key thing here is only, phosphorus and oxygen, is found to have 114.3 grams of oxygen. What is the percent composition of each element in the compound? So what are we given? We're given the total mass, which is 225 grams. We're also given the mass of oxygen, which is 114.3 grams. So we can start off by finding the percent composition of oxygen, which is the part 114.3 grams, divided by the whole, which is 225 grams. Then we multiply by 100. When you calculate it, that will give you 50.8% oxygen. Now you want for the other element, which is phosphorus. So only two elements. So again, percent of phosphorus would be equal to 100 minus 50.8, since a percentage is out of 100. So the percentages of these two elements must add to 100. That leaves us with 49.2%. In this example, we're asked to calculate the percent composition of each element in ammonium carbonate. Now, you will see if it asks you to calculate the percent composition of ammonium carbonate, it means each element. I put this in here so that you can understand that if I ask you to calculate the percent composition of ammonium carbonate, it means for each element. So the first thing we need to do is write the formula for ammonium carbonate. That is NH4 2CO3. So you should know this by now. So let's look at nitrogen. We have 2 atoms of nitrogen, so that's 2 times 14.007. So we need to find the formula mass because we don't have it. That would be our whole, so that's 28.014. For hydrogen, we have 8 atoms times 1.008. So that's 8.064. For carbon, we have 1 atom times 12.011, so that's 12.011. And oxygen, 3 atoms, so times 15.999. That gives us 47.997. So we go ahead and add all these together, and we get 96.086. That's in grams per mole. Alright, so now we need to calculate the percent composition of each of the elements. So let's start with the percentage of nitrogen. That would be 28.014 divided by the whole, which is 96.086 times 100, and that gives us 29.1%. Percent of hydrogen, 8.064 divided by 96.086 times 100, and that gives us 8.4. Alright, our percent of carbon, 12.011 divided by 96.086 times 100, and that gives us 12.5%. All these are in percentages. And last but not least, percent of oxygen is equal to 47.997 divided by 96.086 times 100, and that gives us 50.0. Now if you go ahead and add all these together, you see that they add to 100, so it is a logical answer. Also, oxygen contributes the largest mass, so it has the largest percentage. Hydrogen contributes the lowest mass, so it has the lowest percentage. And if you look at it like that, think about it. Is my answer reasonable? Is your answer logical? Does it make logical sense? Then more than likely it will be correct. So here we're asked to calculate the mass of iron in grams present in 150 grams of iron 3 phosphate. So we first find the formula for iron 3 phosphate. Remember, it's iron 3, so that's plus 3. Phosphate is PO4 minus 3. So the formula is FePO4. So first we have iron. We have 1 atom times 55.84 55.845, so that gives us same 55.845. Phosphorus 1, and that's times 30.974. For oxygen, we have 4 times off 15.999, and that will give us 63.996. We add all these together, we get 150.815, and that is in grams per mole. And we can leave it like this for now. So how do we move from here? We have the formula mass. Now we want to find how many grams of iron we have in 150 grams of iron 3 phosphate. So we have to do a dimensional analysis. Just look at what we're starting with, look at what we're going to end with. So we start with 150 grams of iron 3 phosphate. And we want to convert that into grams of iron. And if we want to get grams of iron, we need to divide by grams of iron 3 phosphate. So we divide by grams of iron 3 phosphate. So what is the relationship we just discovered between grams of iron and grams of iron 3 phosphate? So in 150.815 grams of iron 3 phosphate, we have 55.845 grams of iron. Now remember, this cancels with this, so all we are left with is grams of iron. Alright, so we go ahead and we calculate now, and we will get 55.5 grams of iron. Okay, so that takes us to the end of percent composition. Alright, until the next time, I'm out. Blessings.